In engineering school, you calculate exact insulation thickness or size motors for peak efficiency. But in the professional world, the math changes. The ultimate constraint on any design isn't the laws of thermodynamics or material science, it is capital. If an incredibly efficient design costs too much to build, it stays on the drawing board. Look at a massive infrastructure project like the Hoover Dam. To generate a single watt of electricity or irrigate a single acre of land, investors had to pour tens of millions of dollars into a Nevada canyon. That is a monumental negative cash flow right at the start. You spend millions today in the design and building stages. The benefits, revenues, and cost savings only materialize after construction is finished, and they trickle in slowly over years, sometimes decades. Bridging that gap between present costs and future realities requires a specific type of math. We call it engineering economics. A dollar in your pocket today does not have the same value as a dollar promised to you 10 years from now. This principle is known as the time value of money. You can think of it as a decay rate for capital. As a promised payout gets pushed further into the future, its present value shrinks. This happens because of opportunity cost. If your money is tied up waiting for a future return, you lack the liquidity to invest it elsewhere right now. You are sacrificing other choices. Corporate accounting systems will tell you exactly what you spent yesterday, but engineering decisions require forward-looking projections. You have to estimate future maintenance costs, future salvage values, and future interest rates before a project even begins. This temporal math determines exactly which engineering projects are worthwhile and which ones are rejected by management. To evaluate a physical structure, an engineer draws a free body diagram. To evaluate a financial project, we draw a cash flow diagram. This horizontal line represents the project timeline, starting right now at year 0. First, we plot the costs. The initial investment to build the project is a large downward arrow at year 0. Then we add smaller downward arrows for periodic maintenance in the following years. Next, we plot the benefits. Upward arrows starting in year 1 show the revenues or cost savings the project generates over its life cycle. The sign convention is simple. Money leaving the firm is negative, drawn downward. Money entering the firm is positive, drawn upward. By organizing costs and benefits onto this timeline, a complex mess of variables becomes a clear visual map that can be mathematically solved. This is the future value formula. It calculates how a sum of money today, the present value, grows over time. The variable t is the time horizon, or the number of periods you have to wait. The r is the discount rate, which represents the opportunity cost of waiting. Let's apply this to a design choice. You need to specify a motor. Pump A is cheap right now, but uses a lot of electricity. Pump B is more expensive upfront, but it is highly efficient and reduces your annual energy bills. If you simply add up the purchase price and 10 years of energy bills, you will get the wrong answer. That ignores the time value of money. Instead, we use present worth analysis. We take those future energy costs and run the formula in reverse, discounting them back to year 0. Notice how those future values shrink as they are pulled back to the present. When every cost and benefit is converted to its equivalent value today, the true picture emerges. Pump B, despite its high initial price tag, becomes the mathematically superior choice over its lifespan. This concept is called financial equivalence. It allows you to compare vastly different designs with completely different cost structures on a perfectly level playing field. Money is an active variable in your designs. It has a velocity and a trajectory that you must calculate alongside physical loads and thermal stresses. These exact same mechanics also govern your personal finances. When you invest in a 401k or a health savings account, you are using the time value of money to generate returns for your own retirement. Being able to speak the language of both physical mechanics and financial metrics is a rare skill. It elevates an engineer from a pure technician to a strategic leader within an organization. To justify your designs, secure funding from management, and actually get your ideas built, you have to prove their economic viability. Understanding the time-money continuum gives you the power to decide what moves from the drawing board out into the real world.